Okay, welcome to lecture here. We'll continue on with chapter 12, where we left off. And again, in the chat box, if you could type here for roll, that would be great. Okay, so we've been talking about chapter 12, and a reminder that if you do have questions throughout, you're welcome to, if you like, unmute yourself and ask the question. Again, reminder, video will pop up if you do that, or you're welcome to do it in the chat box. Either way is perfectly fine. I'll be happy to answer your questions. We started talking about kinetics here in chapter 12. And remember, the kinetics basically is the study of how sort of fast or slow a reaction occurs. And we talked about the rate expression, and the rate expression is basically the change in concentration over the change in time. And when we talk about it in terms of reactants, we do negative as they are decreasing with time. So we expect that their concentrations would be going down as time of that reaction occurs. While on the product side, we would also do it positive or keep it positive, again, because we would assume that the product should be increasing with time as that reaction takes place. Remember that when we do the rate expression as well, that you do want to do 1 over the coefficient. And as we talked about with a couple of those examples we did last time, that essentially takes care of all of the stoichiometry, the mole-to-mole relationship that you need to do by doing that 1 over the coefficient. We also did an example as well, or saw that, you can do it sort of as a regular stoichiometry problem and do sort of the mole-to-mole relationship, and then tie in sort of the kinetics part, or the time and the change in concentration at the end. A couple of things about that, again, is that the overall average rate is the same for everybody in that reaction. So the benefit of sort of the rate expression is you pretty much can figure out how everybody is changing with time if you pretty much just know one thing, either the rate, you know how a reactant is changing with time, you know how a product is changing with time, and you're able to do, you basically figure everything out. Then we sort of moved into, towards the end there, the rate law. And the rate law is a little bit different. The rate law does really only deal with the reactants, as the reactants are sort of like the most important thing in terms of the rate of a reaction, especially obviously in a one-way direction sort of reaction. It's obviously the reactants that are important because they have to come together to make products. So in the rate law, one thing that's a little bit different is, as we see here on the screen, it is only the reactants involved in it. So no products in the rate law. And for example, in this generic equation that we see here, as we talked about at the end last time, the rate equals that little k. A reminder that the little k is the rate constant, and sort of like how fast the reaction is taking place. You kind of think about it that way. So the rate equals k times concentration. Again, the brackets mean concentration. It usually means molarity of A to the X and concentration of B to the Y. And again here, X and Y are what are referred to as orders, sort of the proportion you need of those reactants to maintain a specific rate. X and Y are not the coefficients, though, in the balance equation, and we do have to find those experimentally. So usually in these sort of problems, you're given a table of data, and in that table, there's basically concentrations of all the reactants given. There's also initial rates given. And you can sort of analyze it if you want, and sort of see what's happening as the concentration changes and the rate changes. Or most people, like we sort of finished up on last time, take more of a mathematical approach to it, which is what we have up here on the very top. That you could basically take rate 2 over rate 1 equals the rate law for each of those things. And what that means is, in a table like the made up one I did on the bottom there, you will have several entries, could be 3 entries, 4 entries, 5, however many entries there are. But basically what you want to do when you go to that table is choose 2 entries. And the goal here is to have really just one unknown. So when you choose your two entries, what you're looking for is one entry where one of the reactants remains constant in terms of their concentration and the other one varies. Well, once you do that, then you would go back to the table and find two other entries. Again, these two other entries would be where the other reactant remains constant and the first guy now varies. And you could do that sort of relationship. In general, if you sort of take the larger rate on top, you usually will get more of a whole number. You don't necessarily have to get whole numbers, but that kind of makes them sometimes a little bit easier. And again, you can kind of solve for what X and Y is individually. Once you do that, you'll have the orders for A and B, for example, and you can figure out the overall order of the reaction, which is just adding those two together. And you could also figure out the actual value of the rate constant by going back to the table. Any questions on any of that stuff that we sort of talked about last time? Okay, so let's actually look at a real one here with some real data and stuff like that and see what we come up with here. So taking a look at this particular one here, if we have this reaction and we're given sort of this data table here, which again is sort of a common sort of table that you're given. You have the concentration of your reactants. You also have the rates given as well. So we want to basically go to this table and we're going to kind of solve this mathematically. We could write our generic sort of rate law for it, where the rate would equal K times F2 to the X and ClO2 to the Y. And the goal here really from the table is to figure out what X and Y is first. So we're going to use that table to help us figure that out. So when I go to this table, what I want to look for first is two entries like we talked about where the concentrations of one of the reactants remain constant and the other one varies. So if we look at 1 and 2 here, the concentration of F2 remains constant and the concentration of ClO2 does vary. So we're going to start with entries 1 and 2 here. And when I look at this, the rate of number 2 is larger than number 1. So for me, I'm going to put all the information for number 2 on top. Again, usually what that will do is sort of give you a nicer whole number type of approach. It doesn't really matter. You can do it the other way. But again, it gives you sometimes a much better sort of numbers at the end. So up on top is going to go everything that is from entry number 2. So I'm getting old. I think that says -3. And that's going to equal K times our 0.1 to the X and our 0.04 to the Y. So again, everything I just put in there up on top all came from the second entry. I'm going to do the exact same thing for the first entry. So I'm going to put its rate on the bottom. And then I'm going to put the concentration of my ClO2 on the bottom as well. And that's going to give me 2 is equal to, as we talked about last time, although we do not know the number of K at this point, since K is a rate constant, we know that it's going to be the same number. So these are going to cancel. Again, here, we don't know what X is at this point, but we do know, again, it's the same equation or reaction. So it is going to be the same number. So we know that this is going to completely cancel out as well. Now, when we get down over here, we will get 4 to the Y. And I think I did some bad math there. That's actually a 4 on this side. It's like 2, but not so much. There we go. So when we divide 4.8 times 10 to the -3 divided by 1.2 times 10 to the -3, we do get 4 in that case. And obviously we get 4 on this side when we do this guy. So at this point, you can kind of easily see that Y would equal 1. Again, if it's not a nice, pretty numbers like this, you maybe can't figure it out. The way you could really solve it is to take the natural log of 4 on this side, take the natural log of 4 on the other side. When you do that, the Y will actually drop down. And obviously you can divide both sides by the natural log of 4. And as you can see, is Y is equal to 1 in this case. Again, if you have a little bit, maybe not so straightforward numbers, you may have to do that approach to solve it. But obviously, probably just looking at it, obviously here, you would be able to determine that y is equal to 1. So at this point, what we just did is we just found the order with respect to y, and that's with respect to ClO2 in this case. So now what we want to do is go back to our data table. And since we held the F2 constant the first time, what we want to do now is hold the ClO2 constant this time. And when we do that, it looks like entry number 1 and entry number 3 will do that. It's going to hold the ClO2 constant. So we're going to look at 1 and 3 in this case. We're going to do the exact same thing. So again, I'm going to put the larger rate on top, which looks like it is entry number 3. So everything from 3 is going to go up on top. So we're going to go with 2.4 times 10 to the minus 3. It's equal to k, our 0.2 to the x, and our 0.01 to the y. And again, everything there came from entry number 3. Entry number 1, again, is going to go on the bottom here. So that's going to be 1.2 times 10 to the minus 3, k, and 0.1 to the x, and 0.01 to the y. So here I'm going to do better math. We're going to go with a 2 on that one. And that is, again, going to be k is going to be the same. When we divide our guys here, 0.2 divided by 0.1 gives me 2 to the x. And again, this guy is going to completely cancel out as well. You can also see here that x would equal 1 in this case. So we have now basically figured out the orders for both F2 and ClO2. We can write the completed rate law at this point, which is the rate is equal to k times F2 times ClO2. And this would be the completed rate law. Again, much like everything else in chemistry, if it's a 1, you don't have to put it up on top, but just assume to be a 1. The overall order for this reaction can be found by adding the orders that we just found, which in this case is 1 plus 1 equals second order. So overall, this reaction is a second order reaction, which we'll talk about a little bit later on what that sort of means. Now, the last thing that you could do at this point, once you have completed the actual rate law and found the orders, the last thing that you could do actually is now you could go back and actually determine what is the value of the rate constant. So that's sort of the order that you got to do it in. You can find the orders of each of the individual reactants, get the completed rate law like we did here. And now that we have the completed rate law, we could use it to actually find what the value of k is. So if I do that, I'm going to take my completed rate law and I'm going to solve for k. And if I do that, k would equal the rate divided by the concentration of F2 and the concentration of ClO2. So you may ask yourself, where do I get these numbers from? And where you get these numbers from is the table. You could choose any entry you like. You could choose entry 1, you could choose entry 2, you could choose entry 3 from the table. And you basically could just put the numbers in there and solve for k. The only thing you can't do is mix and match. So obviously if you choose entry 1, you have to use all the information from entry 1. If you use entry 3, all the information from entry 3. So here I'm going to use the information from entry number 1, which is 1.2 times 10 to the minus 3 molar seconds, divided by the concentration of F2, which is 0.1 molar, divided by the concentration of ClO2 for entry number 1, which is 0.01 molar. And if we do all that good stuff there, 1.2, I don't know if we talked about it last time, but do make sure you use your exponent button. Hopefully, you know you do have an exponent button on your calculator. And just in case you don't know that, by the way, your exponent button is your EE button, your EXP button, and you should be using that when you do anything in scientific notation. Again, you should not be doing multiplication, inverse log, or anything like that. So if you're doing that, then you are probably entering your numbers in wrong. And what you will get in this case is 1.2 for the number. Now, in terms of the units, the molarity on top cancels with one of the molarities on the bottom, and we are left with 1/molar seconds. And that is a common unit that we see for the rate constant for a second order reaction, 1/molar seconds. Another way you can express that is you could say m-1 s-1 if you like as well. So that's another way. Again, you can sort of put the units in there. Any questions on any parts of that calculation, where we got the numbers from, why we did anything?
All right, I came in a little bit late. What does K represent?
K is the rate constant. So it represents the rate constant, which is constant for a reaction, sort of the how fast the reaction is occurring. You kind of think about it. Other questions?
What is the word or numbers above like 4.8 that you underlined? It looks like LAN. Where is that wrong?
Hang on a sec here. That's the you're talking about over here where it says LN?
Or not LN, it's like above LN. It's like the first, it's what you underlined and it looks like LANR2 or something, or
It says 1 and 2.
oh, it says 1 and 2. Oh, okay.
Sorry, yeah,
Oh, I see it. Okay,
yeah,
got it.
Okay, yeah.
All right, thanks.
Still getting used to writing on the screen here. Other questions on anything? Okay. So again, this is sort of the order of how you want to approach these problems. You want to really use the table to figure out the orders of each of the reactants individually. Once you get that, then you have pretty much everything that you need to figure out the rate constant, and that's a typical sort of way that you do this. Again, in this case, we only had 3 entries in the table. Sometimes you may have more, but you should always have enough entries where you could kind of keep one constant and vary the other. In addition, most reactions probably usually don't have more than 2 reactants. Some do. So it's possible you could have, for example, 3 reactants happening, and you may have information about 3 concentrations. And in that case, you would want to keep 2 constant and vary 1. So the key is just to have 1 unknown or 1 concentration that varies. All right. So as we saw there, a couple important things about the rate law, that the rate laws are always determined experimentally, which means really in these type of problems, you will be given those tables, and those tables will have that information in it, the concentrations, the rates, and all that kind of things. The reaction order is always determined in terms of the reactants, so no products in a rate law. In the rate expression, like what we did last time, you could have products in there, but here when you're doing rate laws, it's just reactants. And as we saw in this example here, the coefficients in the balance equations do not equal the order. So you can see here ClO2's coefficient was 2, and the order there for ClO2 was 1. So your question about larger rate over smaller rate, and again, you don't necessarily have to worry about that, but it is just simply the number. So for example, when we looked at these rates here, just simply this number, for example, is larger than this number, just comparing them. And that's how you could determine that one is the larger one. And like I said, if you typically put that one on top, you'll get more of a whole number when you sort of do the dividing. You don't have to do that, like I said, because you can do the smaller numbers. You just get more of a decimal number, and then you could use the natural log or something like that to figure out, what X and Y is. So in terms of determining which one's the larger, it simply is just that whichever number is larger, essentially. All right. So why don't you, so here, I want you to do this one real quick here. The rate equation for NO is the rate is equal to KNO times O3. If the rate is 6.6 times 10 to the minus 5, when the concentrations are each of those, calculate the rate constant. So see what you come up for the rate constant just to make sure. Okay, so this one here, we're given the rate law, so we're not to calculate at least. So we got the rate is equal to K times NO and O3. We're assuming in this case, again, not usually written, each of the orders here is first order for each of the reactants. Overall, this reaction is second order overall. Again, determined by adding those two numbers together. You don't really even need to worry about that in terms of this particular question, just kind of summarizing it though. Again, here, since we're looking for K, we would take K would be equal to the rate divided by our NO concentration and our O3 concentration. So really just need to plug into here our numbers. So 6.6 times 10 to the minus 5 molar seconds divided by our 1 times 10 to the minus 6 molar and our 3 times 10 to the minus 6 molar. And again here, unit-wise, molarities will cancel. And if we do that division there, we got 6.6. Again, make sure you use your exponent button. That's the E button. Use your negative button, not your subtract. Minus 5 divided by 1 exponent button, negative 6 divided by 3 exponent button, negative 6 as well. And that gives you 2.2 times 10 to the 7 molar seconds. Probably should have a 0 in there as well. Any questions on that particular one there? Again, in terms of sig, figs, everybody's got 3, so that's why I threw the extra 0 in there. And in terms of the units, that is not the correct unit. So when we actually put the correct units, it is 1 over molar seconds. Sorry about that. Again, the molarities cancel, leaves us 1 over molar seconds. And again, that is a common unit for a second order reaction. So we'll talk about this a little bit later on in this chapter, but the actual units that you see for the rate constant is very helpful later on to determine what the order of the reaction is. And as you can see here in the last two that we did, they were both second order, and the units of the rate constant were 1 over molar seconds, which is common units associated with a second order reaction. So again, things like units that you'll see in this chapter for things like the rate constant are really important to determine the actual order of the reaction in terms of what's happening. All right, so why don't you try this one here? We got some table values. So here we want to determine the actual rate law with the correct orders for everybody, and also the value of the rate constant. So why don't you take a couple minutes here and see what you come up with, and then we will talk about it. So again, we want the completed rate law with the orders for each of those guys, and also the value of the rate constant. So see what you come up with. And like I said, we'll talk about it in just a second. Okay, so let's take a look and see how we're doing. So again, here we have a table of some information of molarities and rates. So what we want to do is, again, try to figure out one where, or two entries where one stays constant, the other one varies. So again, here we can look at 1 and 2, and we see that the S208 remains constant while the I minus varies. We could start with our sort of generic rate law where it's just the rate is equal to K times the S208 2 minus to the X and our I minus to the Y. So again, the goal here is to figure out what X and Y are. And we're going to do that by, again, mathematical here. So I'm going to look at 1 and 2. And when I look at 1 and 2, for me, again, I'm going to go with number 1 on top in this case because just simply the rate is larger. So again, should give us more of a whole number, which makes it a little bit easier sometimes. So we got 2.2 times 10 to the minus 4 K times our 0.08 to the X and our 0.034 to the Y. Again, all that information is from entry number 1 in the table. I'm now going to put all of entry numbers 2 in there, and that gives me 1.1 times 10 to the minus 4, our K, our 0.08, and our 0.017 in this case. Again, when we divide these guys here, we get a 2. Just like we've been talking about, the K is a rate constant, so it will be the same on both, so they cancel. Again, we don't know what X is at this point, but it is going to be the same number, so this will also cancel. And when we divide out the back end here, we will get there 2, it looks like, 2 to the Y. Again, in this case, Y will equal 1. So by doing this here, we now found the order with respect to I minus in this case, and it happens to be first order with respect to that. We now want to go back to the table and we want to keep I minus constant while varying the first one. So in that case, it looks like entry number 2 and 3 will do that for us. So if we look at 2 and 3 here, again, doing the same sort of approach, I'm going to do entry number 3 on top just simply because it's a larger rate when comparing the two. And again, that will give me a little bit nicer numbers in most cases. I won't say 100% of the time, but in most cases, it will do that for you. 0.16 to the X and 0.017 to the Y. And now we're going to put everything from entry number 2 on the bottom. And that's going to give me 1.1 times 10 to the minus 4, K, 0.08, and 0.017 to the Y. When we divide this guy, we'd get a 4. Again, the K is going to be the same. When we do 0.16 divided by 0.08, that looks like that's a 2 to the X. And again, this guy is going to cancel as Y is the same for each of them. In this case, you can see that X should equal 2 in this case. Any questions on that so far? So that is our order with respect to the S208 2 minus. Now that we have the order for everybody, we can write the actual completed rate law with the orders, and it would be in this particular case that the rate is equal to K S208 2 minus to the second and our I minus in this case. Also means that the overall order here would be 2 plus 1 would be a third order reaction in this particular case. Any questions on that so far? Now, once I do have the completed rate law, I then could go back and use the table to figure out the actual value of the rate constant. And what I'll do is I think, let me just go here. I think an extra page. Let's go back here. So our rate law was that the rate is equal to K times S2O8 2 minus, and that was squared, and I minus. So in this case, rearranging and solving for K, K would equal the rate divided by S2O8 2 minus squared, and I minus. So again, in this case, you could choose any entry you like from the table, and it should come out the same. So here I'm going to choose entry number 1. So from the table and entry number 1, we see that we have a 2.2 times 10 to the minus 4 molar seconds divided by our S2O8, which is 0.08 molar. And again here, because it is second order with that guy, we do need to square it. And our I minus, which is 0.034 molar in this case. And if we do all that, we will end up with 2.2 exponent minus 4 divided by 0.08 squared and divided by 0.034 gives us something like 1.0. And the units now are molarity here. We'll cancel a molarity here. 1 over molar squared seconds would be the units. Again, we have to also square the M here as well. That's where the squared part comes into play. Any questions on that? You could also see that this was technically a third order reaction. Probably doesn't happen very often, but it does also have different units than what we saw for our second order for the value of K, which is 1 over molar seconds. Any questions on any part of that? Yeah.
I have a question.
Yeah.
So when we find K, do we put it in like the final, like the rate, like that final equation, or do we leave it as K?
You can do that. So if you're asked, you could do it either way. You could, if you're asked what the rate law is, you could go the rate is equal to, like it is on top there, K and the S2O8 squared. Or you could, if you did find the value of the rate constant, actually put the number in. Either way is perfectly fine. You could do it either way.
And you put the number in with the units if you are putting
You would, yeah. So you typically would want to put the units in with the rate constant. The units are really important with the value of the rate constant or the unit of the rate constant. Again, it does tell people sort of the order of the reaction and stuff like that. So you should always keep the units with it.
Okay, thank you.
You're welcome. Other questions on anything like that? Okay. And again, if it was sort of a question like this, the way I just did it here would be perfectly fine. If I asked you what is the, completed rate law with the orders, if you just wrote it like this, that would be probably perfectly okay for me. Again, because probably in that question, I would ask you the secondary question of, what the value is. So along the way, but again, you can actually substitute the number in. It's perfectly fine. All right. So why don't you try another one, which I think maybe is this one. Oops. All right. So why don't you give this one a go and see what you come up with. Okay, so let us work our way through this, see how we're doing. So again, same approach here. We're going to take a look at our rate law, which in this case would be NO2 to the X and CO to the Y. Again, just our reactants involved. In this particular case, we have multiple entries. We got 4 entries. Again, doesn't matter how many you have in the table. You're just going to kind of take the same approach. So just looking right here at entry number 1 and 2, we have the CO that's constant. So we can look at the NO2 in this case. And again, 1 and 2. That means I'm going to put the second one up on top, so it looks like it's a little bit larger of a number. So 0.0082 equals K, our 0.2 to the X, and our 0.1 to the Y. And now everything from 1 on top, on the bottom there, 0.0021, 0.1, and 0.1, it looks like. All right, so in this particular case here, we got 0.0082 divided by 0.0021. It gives us something like 3.90 is equal to the K's cancel. This is going to give us a 2 to the X, and these guys will completely cancel out. So really, again, in this situation here, mathematically, if you want to kind of solve for it, what you can do, if you can't really figure out what it is this is pretty close to 4, right? So pretty much X would equal 2. But again, in case you're not sure, you really don't want to do it that way, you could take the natural log of 3.9 would equal the natural log of 2. And again, when you take the natural log, the X will come down. You then can divide both sides by the natural log of 2. This guy will cancel, and this will give you, when you do that, the natural log of 3.9 divided by the natural log of 2 gets you something like 1.96, which again, for our purposes, you could round up to 2 in this particular case. Any questions on that there? So again, you can do a little bit of rounding. It is experimental information, which means it doesn't always come out perfect. I will say in a lot of textbooks, it will probably come out perfect, but not 100% of the time. So again, the correct way really is to kind of take the natural log of both sides, or even the log of both sides will get you there. All right, so now that we got the 2 there for our NO2, we want to keep our NO2 constant and then vary our other guy. And in that case, if we look at entries number 2 and 3, looks like it will do that for us. So entry 2 and 3, and again here, let me just grab something to go with here. Just put it right on. There we go. So if we go with entry number 2 and 3 from the table, and entry number 3 looks like it's just slightly higher, so we'll put that on top. So 0.0083 equals K, and we have 0.2 to the X and 0.2 to the Y as well. And entry number 2 there, we have 0.0082 K and 0.2 to the X and 0.1 to the Y. In this case, this is essentially 1, and this will cancel out. These guys will cancel, and at the end here, we will get 2 to the Y, I believe. Yes. So in this case, when we go to solve it, hopefully you know that if you take something to the 0 power, that will equal 1. So Y here would equal 0 in this particular case. And again, if you're not sure, you can take the natural log of 1 and divide it by the natural log of 2. When you take the natural log of 1, it equals 0. So 0 divided by 0.693 equals 0. and 0 would actually be the order here for y. Any questions on that particular one? And again, if you're not sure, you can take the natural log of 1 and natural log of 2 drops the y down. Natural log of 1 is equal to 0, by the way. And if you divide that, those cancel, and that equals 0. All right, so at this point, we now have the orders for everybody. We got the rate law would look something like the rate is equal to, it looks like K times NO2, and it would be squared. And because the CO is a order of 0, you don't necessarily have to include it in there because technically speaking, if you wrote CO to the 0, that basically is 1. Yeah? So most of the time people will not include it. If you do include it, if you want to include it, you do definitely in this case need to put the 0 there. Otherwise, if you just wrote CO, it would imply that it is first order and stuff like that. So if you do include it and it's 0, and again, you don't really need to, you definitely need that 0 there to indicate that it obviously is a 0 order and not 1. So make sure you keep that in mind. Now at this point, we can solve for the value of the rate constant. So in this case, rearranging, K is going to equal the rate divided by our NO2 squared. And just like we've been talking about, you pretty much can choose any entry you like. So I'm just going to take number 1 and go 0.0021 molar seconds divided by my NO2, which is 0.1, and again, not forgetting to square it, and that's molarity. And if I do that, 0.0021 divided by 0.1 squared gives me 0.21 units. One of the molarities will cancel. We get 1 over molar seconds, which is okay because the overall order here for this reaction is 2 plus 0, which is second order. So again, second order reaction, those are the typical units that we associate with it, and it all makes sense. Any questions on any of those steps? So that's something that does come up a number of times. Again, something to 0 order is 1. Any questions on that?
I'm sorry, just to be clear, what exactly does it mean for it to be like a second order reaction?
We're going to talk about it in a little bit, but essentially it's sort of the way the reactants come together in terms of the rate. So for example, there's 2 ways you could be second order. You could basically have one like we have here in this particular problem here, where even though there's 2 reactants, the only thing that really affects the rate, as you can see from the rate law, is actually the NO2 concentration squared. The concentration of CO in this particular case has really no effect on the rate, as you can see, because it's 1. So it's not really doing much in terms of the rate. So in this particular reaction, the one that really determines how the rate happens or how fast it happens is the reaction of really the NO2, sort of the concentration of the NO2 has the most effect on the rate. Now you could have a second order reaction where both of the reactants are first order, so 1 and 1. And in that case, the rate is determined by both reactants in that case, sort of their concentrations coming together, and the concentration of each of them will have an effect on how fast or slow the reaction will occur. So that's sort of what first order, second order, and 0 order sort of means. It's sort of the way the reaction sort of comes together and what's really important in terms of the rate of the reaction. So as you can see here, the concentration of CO, you could change it to whatever you like. It will have no effect on the overall rate of the reaction. Other questions? Okay, so I think we got one more here. So why don't you try that one? Let's see, where is that thing? There it is. One last one here and see what you come up with. Same deal. Figure out the overall rate law with the orders and also the value of the rate constant. To answer your question, I got that on the last one here. Where did it go? So your question is, where did I get this from? I got this from, since what we did up above here was for CO. So the CO was zero order. And earlier we did our NO2, which was second order. And so that's where the 2 came from. The NO2 squared came from that. So basically doing the same thing, just keeping the CO constant and using the information, we got second order for NO2. And that's where that came from. And again, what we calculated was that the CO was zero order, which again means that in terms of the overall rate of this reaction, once we figured out those orders, it's really only the NO2 that has an effect on the actual rate of the reaction. So again, because the concentration of CO, its order was 0, anything to the 0 order equals 1. So again, you don't need to include it in the rate law in this particular case. And as we were just talking about as well, what that also means is in terms of the rate, the concentration of CO really doesn't have any sort of effect on the overall rate of the reaction.
Thank you.
Welcome. Okay, so let's see how we're doing. So again, same approach as all the other ones that we've been doing. So let's just start with the rate in this case would equal K, our NH4 plus to the X, and our NO2 to the minus, and we'll go to the Y. And it looks like in this case, we could go with 1 and 2, and that will keep our NO2 minus constant. So looking at 1 and 2, here I'm going to go with the second entry up on top, and we will go with 32.3 times 10 to the minus 7. By the way, don't forget to read the actual headers there. It is times 10 to the minus 7. And we will then go that equals K and our 0.02 to the X and our 0.2 to the Y. Here, we will now put everything for number 1 on the bottom, 10.8 times 10 to the minus 7, K 0.02 to the X there. I think I mixed that up there. And 0.2 to the Y. I think I looked at the wrong entry there. Let me fix that real quick. There we go. All right, so this guy helps if you look at the right line. That should be 0.06. That would be better. 0.06. To the X. There we go. Now I think we're good. 0.02. Perfect. So when we do a little division here, we got 32.3 to the minus 7 divided by 10.8 to the minus 7. Gives us something like 2.99. You could probably call that 3. And that's going to equal 3 to the X. Again, these guys are going to completely cancel when we do that division, and really X here is going to equal 1 in that case. Now that we did the NO2 minus constant, we're going to keep the other one constant, and it looks like perhaps 3 and 4 will do that for us. So entry 3 and 4. Again, here I'm going to go with number 4 on top, a little larger of a number for the rate. 21.6 times 10 to the minus 7 equals K R 0.2 to the X and our 0.04 to the Y. Again here, everything I just wrote came from entry number 4. Entry number 3, we're going with 10.8 times 10 to the minus 7 and 0.2 and 0.0202 to the Y here. Again, when we divide these guys here, looks like we do get a 2. K's are going to cancel out completely. This guy will cancel out completely. Here we will get 2 to the Y. Y would equal 1 in this case. So at this point, we've now figured out the orders for everybody, and our completed rate law would be the rate is equal to K NH4 plus and NO2 minus. Again, each of those to the first order. That means overall, this reaction is second order overall. Again, that is found by simply taking 1 plus 1 equals 2. And that is the orders, the X and the Y that we found in this particular case. And lastly here, to kind of finish up this one, the last thing that we do want to find is the actual value of the rate constant. And just like we've done before here, we can take any of the entries and do that. We're just going to rearrange our rate law and solve for K. So K would equal the rate divided by concentration of NH4 plus and NO2 minus. And again, here you can choose any entry you like. So here, let me mix it up. We'll go with entry number 2 this time, and we're going to put the information in. Now, if you earlier kind of forgot about this part and just used these numbers, you will see that you got the same orders as I did, and everything comes out the same. The place where you really will not get the right answer in this case is you will not get the right answer if you did not put the times 10 to the minus 7 for the rate constant. So you do want to make sure you look at these tables and everything like that. And we get K is equal to, this is going to be 32.3 times 10 to the minus 7 molar seconds divided by 0.06 molar and 0.2 molar in this case. And if we do that, 32.3, again, don't forget the minus 7 part of it, divided by 0.06 and divided by 0.2. Looks like it gets us a rate constant of, we'll go with 2.69 times 10 to the minus 4. Now, in terms of units, molarity up on top and a molarity on the bottom will cancel. And I'll just write them down here. 1 over molar seconds would be our units. And again, hopefully you can see a theme. We had a number of second order ones along the way. And again, they do end up with the same units, the 1 over molar seconds. Or again, you can write m to the minus 1, s to the minus 1, which would be the same. Any questions on any of those steps? And again, a very important thing, sometimes in tables, they do things like that to make sure your table is not super big or something like that. So make sure you actually do look at those things. Again, in this case, if you miss the times 10 to the minus 7, really the part where it will affect your answer is at the end there. You will be off in terms of the actual rate constant. It won't affect anything really in here because the 10 to the minus 7 divided by 10 to the minus 7 cancel each other out. So taking 32.3 divided by 10.8 are taking 32.3 times 10 to the minus 7 and divided by 10.8 times 10 to the minus 7 will come out to the same. Any questions on any of those steps? How to calculate the orders, the rate constant from data given to you? Again, very common. That is exactly how you do figure out the rate law for a reaction, is to use this experimental information. Any questions on it?
Question.
Yeah.
Why is it that you chose 32.3 times 10 to the negative 7 for the rate?
When I was solving for the rate constant at the end?
Yeah, the last part in blue.
Yeah.
The rate.
So once you get to the part where you're going to solve for the rate constant, you could choose any entry in the table you want. So I just did it to sort of vary it up. So I could have chose entry 1 like I've been doing. You could choose entry 2, you could choose entry 3, you could choose entry 4. In this particular case, I chose entry number 2, which is why the rate was 32.3 times 10 to the minus 7 for that particular one.
Got it. Thank you.
Yep. And again, you can technically, if you went through and did every single entry in this table and put it into the rate constant, you should get the same number. And hence, that's why the name of it is called basically the rate constant. It should be constant for that particular reaction under those conditions. So that's why you can technically use any entry you like from that table. The only thing you can't do is mix and match. So you got to do all the, like I did, everything from entry number 2 in there. And then you could, or if you wanted to, everything from entry number 1, entry number 3, and so forth. But technically, even if you go back on all the examples that we did previously, if you wanted to find the value of K, you could have done any of the other entries in those tables, and they should come out to pretty much the same number. Other questions?
Oh, okay. So I'm still not 100% understanding like how like what order reaction this is, like what does that do?
So I'm sorry, say it again. You don't understand.
I'm still not like fully understanding how like it matters, like this is like a second order reaction, right?
Right.
Like I'm still not getting what that does.
Yeah. So again, really what it means is, in this particular one, different than say the second order that we saw on the previous example. On the previous example, if we go back, for example, here, where's that guy? Right here. So this one was also a second order reaction as well, right? And if you look at the the reaction that was going on in this particular one before I scribbled all over the page. We had basically two reactants, right? So we had the, what's that, NO2 and our CO, right? And basically what we determined after figuring out that this was a second order reaction and the actual rate law from it was that based on the rate law in this particular reaction, the only reactant concentration that really affects the rate is just the NO2 because the CO's order was 0. And what that means is if you want to affect the rate, if you want to say increase the rate, decrease the rate, whatever it may be, the only one that really will basically determine how fast or slow the reaction will occur in this particular reaction, the way it occurs, is really just the NO2, as you can see here. It's just the NO2 is the only thing in the actual rate law. The CO, again, is 0 order, which means it's, I don't want to say constant, but it really won't have an effect on the actual rate, how fast this reaction will occur. Now, if we look at the one that we just did, which is also, where is that? There, which is also second order. But the difference between, say, the second order we just saw and the second order we're looking at in this particular reaction is, in this reaction, there's two reactants, just like there was in the previous one. But based on what we see here in the data, it suggests that the overall rate law is the NH4 plus times the NO2 minus. What this means is that both of these guys, both reactants in this case, have an effect on the rate. So if you vary, say, the NO2 minus, it's going to affect the rate. If you vary the NH4 plus, it will affect the overall rate of this reaction, how fast or slow it will happen. And that's different than the previous one here, where you could pretty much do whatever you like with this guy because it will have no effect on the rate. It's really only the NO2. So when we talk about sort of the overall order of a reaction, first order, second order, 0 order, what we're sort of looking at is, you know, what in that reaction in terms of the reactants will have an effect on the actual rate of that reaction, how fast or slow it happens, what concentrations will really have an effect on, again, how fast it will occur or how slow it will occur. So here in these two examples, although they both are technically both second order reactions, this particular one we're looking at right now, both reactants play a role in the actual rate of that reaction. While in the previous one, it was actually only, what was the other one? NO2, I think. And the previous one was the only one that really plays a role in how fast or slow the reaction will take place. So, you know, that's sort of what the orders, you know, sort of represent is sort of the proportion that you need of the reactants to come together to maintain a particular rate. So, you know, in this case, you need to throw in there some NH4 plus and NO2 at an appropriate concentrations to get out a specific rate. In the previous one, you could throw in as much of the other one, the CO, as you want, but it will have no effect on the rate of it. So that's sort of what the orders sort of represent is like, you know, when you're making cookies, for example, you need to throw in there so much of all the ingredients to get out like a dozen cookies, right? If you vary some part of it, like say the flour or something like that, you're going to yield less cookies, right? And that's sort of what the rate law sort of tells you, you know, in order to maintain a specific rate, there's a certain proportion of reactants, right, that you need to put in there. Just like in the cookies, if you want to make a dozen chocolate chip cookies, right, if you cut back on the chocolate chips, you'll still could get a dozen cookies, right? As long as you have the right flour and all that, right? You may not have as much chocolate chips in there, but you'll still be able to produce, you know, a dozen cookies. You may have less chocolate chips. But again, if in the case where you cut out the flour and stuff like that, you're not going to be able to produce as many cookies as you would and so forth. So in the case of that example, you know, the flour is important in terms of how much you would get. And again, in this case, what we're seeing is both of these reactants are important in maintaining the rate of this reaction, while in the previous example, it's only the NO2 that's important in maintaining the rate for this particular one. Other questions on that? Okay. So you do need to obviously be able to figure out all those things, the rate law, the overall orders for each individual reactant, being able to add those together and figure out the overall order, and obviously calculating the value of the rate constant from experimental information. So let's talk about actually specific orders and some equations that go with it. So the first type of sort of reaction we're going to talk about is what is known as a first order reaction. And a couple of things about this that we will see. In a first order reaction, it's like A goes to products, and we have our rate expression there, which is the change in the concentration of A over the change in time. And there's really, again, a couple of ways you could get a first order reaction overall. Like we have here, we have just one reactant to the first order. That would be one way that you could get a first order reaction. And what this would mean is this is typically what happens, for example, in like a decomposition reaction, right? In decomposition reaction, you have one reactant, it decomposes into some things, and it's really based on that one reactant. And that's what this would mean. The rate in this particular reaction would be based only on, reactant A. You could also get a first order reaction where you had a rate law where the rate is equal to K, A to the 1, for example, B to the 0. So as we talked about before, B to the 0 means it's first equals 1. And that essentially gets us back to this rate law here. And in the case like that, if you did have a reaction where it was A plus B goes to products, what this would mean is if B was 0 ordered, as we just were talking about, even though it's involved here and it is a reactant, it will have no effect on the rate of this particular reaction. It is just A that's important in this case. So again, as we talked about, when you think about just chemical reactions in general, in terms of how many reactants you sort of start with, it's very common to have perhaps one reactant, two reactants, occasionally three reactants. But, we don't really get into a lot of reactions where there's like 4, 5, 6, 7, a ton of reactants occurring, all at once, So that's why we commonly will see these sort of orders that we're talking about here, first order, 0 order, and second order, as it sort of relates to the common amount of reactants that we sort of see. So if we take this rate law and we rearrange the rate law and solve for the units, this is really important. Typically, when we have a first order reaction overall, the units for the rate constant are 1 over seconds, or reciprocal seconds here. Now, as I mentioned before, really crucial in kinetics is understanding, are we dealing with sort of a first order, 0 order, second order reaction? And one way that you can figure that out is by looking at the units of the rate constant. And it's really important to understand the different units associated with the orders of reaction, because they will not in flashing lights go, hey, this is first order, this is first order, first order. They will oftentimes just give you the units for the rate constant. And when they give you the units for the rate constant, they expect you to know, oh, those are the units that are typically associated with a first order reaction. So you'll use the correct units when you go and do those equations, or use the right equations when you see those units. Now, when we talk about the units for first order as being 1 over seconds, that is the most common unit for a first order. And it doesn't necessarily have to be seconds. So it can be like 1 over minutes, 1 over days, 1 over some unit of time is essentially the first order units for the rate constant. Why we typically use seconds is, if you just think about it logically, most reactions that we would do probably occur within seconds to minutes. We typically don't do reactions over days, weeks, years, and stuff like that. So usually when people say, what are the units of a first order reaction, they do say it's reciprocal seconds, or 1 over seconds. But technically speaking, it does not have to be seconds. It could be any unit of time you like, but it's just 1 over a unit of time. And when we look at a first order, there's 2 typical plots that go with a first order reaction. The first one here is concentration on the Y, and time on the X. And what we see is a sudden decrease over time, which is what we would expect as the reactants start to decrease. With time, it starts to go down, and we see this sort of curved plot here. Now, typically speaking, this equation here is what is sometimes referred to as the integrated rate law for a first order reaction. And what this equation tells you is, or allows you to figure out, is how concentration is changing with time. So when we look at the natural log of A, this A is sort of like your final concentration. The A naught with the little circle is kind of like your initial concentration. The K here is your rate constant. And this T here is actually time. So sometimes people always think T is temperature, but this is actually time in this case. And if you take this equation and you rearrange it, and you write the natural log of A is equal to minus KT plus the natural log of A naught. This is the form of this equation for a straight line. And if you remember, hopefully, the equation of a straight line, y equals mx plus b. And y is what's on the y-axis here. So we see on the y, natural log of A, which is graphed. On the x is t. And because this is a straight line, like you see here, we do get a straight line with a negative slope. And the slope is equal to minus k. So the slope of that line equals minus k. The y-intercept equals the natural log of the initial concentration as well. And because the slope is negative here, when you would actually calculate it, the negative and the negative k will give you a positive number for the rate constant. So the rate constant should be a positive number, and that's essentially how you get there by the graph. So that is, for the most part, when people say, what does the graph for a first order equation look like? We typically do look at the sort of straight line graph, and we do the natural log of A versus T. So it's really important to know a few things on this slide for sure. First off, you do need to know the units associated with a first order rate law, and you need to know the two graphs associated with it. Again, this graph here is typically the one most people associate with it, which is your natural log of A versus T, gives you a straight line. You do need to know the integrated rate law there, which is our natural log of A equals the natural log of A naught minus KT. And we'll see it in just a second, but or next time, but since we're getting to the end, I'll just put it here just so it's all together. There's actually an equation for the half-life. And the half-life, as we'll talk about, is pretty much what the name implies. It is the time it takes for half of whatever you started with basically to go away. And the half-life for a first order equation is the natural log of 2 divided by the rate constant. And if you do the natural log of 2 on your calculator, 0.693 is what will come up, which is commonly what you will see as well. So the first order integrated rate law and the half-life equation also really important. There's a lot of problems where you have to use the half-life equation with the first order equation there. So it's really important as well. So units for the rate constant for first order, graphs, the two equations there on the top right are definitely the stuff that you do need to know, because you need to be able to choose the right one, because we will talk about probably next time second order and zero order reactions, which have different equations. But again, this equation here allows you to figure out, you know, how the concentration is changing with time. Any questions on that? I think we'll probably wrap it up for lecture here with that. It's a good place to stop. Any questions on anything that we talked about? Okay, so for today for lab, we're going to do a few things, I think. We'll talk some lab safety, talk about lab notebooks. We'll do a couple of things, and I'll see everybody at 11:30. Make sure you come through the lab link, and if you didn't put here in the role for the chat box, make sure you put here before you log off. And I'll see everybody in about 11:30.